Yoko, you want to do the Minty questions?
Yes, sir. So I'm going to share my screen. Here we go. So everybody, please get out your either another tab on your browser or open your phones and go to menti.com, menti.com, and enter the code that you can see on top of your screen, 8080089. And then it's an interactive question answer poll really quick. Kind of a fun way to not fall asleep during a Zoom. Not that we're boring, but it's kind of later in the day. So the first question is, rank these wastewater sources by their wastewater strength, the first being the highest. And the 4 answers you can see on the screen are not the correct order. So let me know if you need help, but I think it should be pretty self-explanatory. Okay, first answer's coming in. 3 answers so far. It looks like everybody has the same idea so far. Let's see if it keeps going like this. I know some people are on their phones, so no worries about that. All right, 5 answers. Okay. Anybody still working on their answer? All right, 6 answers. Very good. I'll give 10 more or 5 more seconds. All right, so yes, this is correct. Very good, everybody. Piggery, highest strength. Restaurant, second highest from the food production and the oils and stuff like that. Residential dwelling comes in regular strength, 3rd place, and public shower facilities, last place, since they are dominated by gray water and not black water. Great job. And then the second and last question coming in here. So that should pop up in your phones right now. So piggeries is an example of a high strength source of wastewater. It's higher than your average. So what other sources? We had restaurants, we had a piggery. What other sources of high strength wastewater can you think of? Got commercial, grease trap waste, distillery, breweries. Good ideas. Industrial, yes, those are all really good answers. Gonna give 5 seconds if somebody else is still thinking of something. Awesome. Great job, everybody. Thank you for participating in that.
All right, now we show the film as we queue up the film. This is a film that was done about our new Cinderella incineration toilet. Forgive the narrator or the key figure in there for his speaking abilities. And this is about HIMB facility we just did. So go ahead.
In terms of health, Hawaii has 4 times the rate of staph infections and 2 times the rate of MRSA infections than the rest of the country. And every single area in Hawaii, cuts across all demographics, has cesspools. And so there are times where we are swimming in our own waste, and that's a huge concern. There's environmental concerns for the reefs and for harmful algal blooms, but there are also health concerns with all kinds of dangerous pathogens in the water.
So we're here on Mokoloi, which is the home of the Hawaii Institute of Marine Biology. We're an organized research unit within the University of Hawaii, and we're housed in the School of Ocean and Earth Sciences and Technology. And we focus on all aspects of tropical marine biology. So we have an incineration toilet that is being installed here on Mokoloi. We're very excited about it because it's an alternative to waste disposal, which essentially burns waste, both solid and liquid, doesn't require any hookups to municipal systems, produces very little emissions, requires no water. All of these things are important considerations. We need to solve the problem of sewage in Hawaii in general.
Here in Hawaii, we have over 80,000 cesspools that still remain, and it makes us one of the most impacted states anywhere in the country. And we're not going to be able to change that out overnight. So we really need new kinds of technology, new kinds of approaches that are going to revolutionize the way that we fund and build sewage systems to address that. We've only got a couple decades to meet our legal requirement, but really we want to move there as fast as possible, because ultimately we know each passing year that you have more and more runoff, more and more leaching of this kind of raw sewage into our streams, onto our beaches. It creates a health hazard for everybody.
We at WAI are committed to finding the most ecological, the most affordable and efficient solutions to wastewater management. There is no silver bullet. So we are trying to bring in all kinds of technologies, including the Cinderella toilet. We're also looking at innovative nitrogen-reducing bioreactors, which are passive systems that do treatment that don't have moving parts. We're also looking at aerobic treatment units that if you live too close to the coast and you're near groundwater, you're going to have to use that. All the way up to Cambrian innovations, which can process up to 150,000 gallons per day. We're excited about Cinderella toilets and their incineration technology, but we have many arrows in our quiver, and we know that this is something that we have to do, and we're committed to helping the state, communities, and homeowners with this transition process. Thanks for joining us. This was our premiere, our brown carpet review. So we appreciate you guys here for that epic release. Any quick feedback before we move on? Okay, we won't be sending it to the
toilet working so far?
It's what?
How's the toilet working so far?
Good, we're getting good reviews.
Nice.
Yeah, we're about to install our second unit at Kualima Farms on the North Shore across from Turtle Bay. And there are a lot of agencies that are interested, and we're going to be having a little small potty party at the farm for the installation. So next week, so if you're interested, let us know. And then also want to let you know we're having a town hall meeting to kind of talk to folks about what we're working on and the cesspool conversion process, and that's going to be in Kahalu'u in Thursday, February 4th. So if you want to attend that, we'll also send out information about it to our CAP group, but just wanted to let you all know in advance. And so now, if there's not anything further, we'll pass it to our guest speaker. We want to thank Michael for joining us today and sharing his years of research at UH. So thank you, Michael.
Well, no, it's me. I'm thanking you for even evaluating and seeing if you can help me find someone who needs it, basically. So thanks is the other way. I've done enough presentations in my life that I don't need to do it anymore, other than in an environment where something good is happening. So thank you very much for having me. I appreciate it greatly. How long do I have?
If you could do 15 minutes, and then we'll leave 5 or 10 minutes for Q&A after that.
Okay. So then I'm going to share it, right?
Yeah.
Can everybody see it?
Yes.
All right. So you have been forewarned that right now, this may not be a good presentation, right? Because I put it right up there in the front page. that this may not be very good. I have to say, in academics, we have a game of acronyms. You know, there's always a game to try to come up with some clever phrase for your research project or your center. And this is honestly the all-time best I've ever seen. You actually beat out Dave Carl, who happens to be the best of the faculty I've ever seen anywhere on 3 continents. But this is the best I've ever seen. So well done, whoever came up with this. So what I'm here to do is to try to explain and present a reactor system that I've designed over 10 years that I think could find a good niche for processing high strength wastewater.
Michael, I'm so sorry. Do you want to go full screen? I think that'll be easier for everybody to read.
Oh, yeah.
Thank you so much.
Can everybody see the full screen now? Great. So I'm trying to present to you a reactor system that I've designed over the years, go many left turns and right turns. I've kind of settled on a system of design I'll show you in a couple of slides that is targeting to treat high strength wastewater, inclusive of slurries and solids within. And it came out of 10 years of work. On the left shows a lab reactors that we ran for almost 5 years. There was 5-6 years of continuous operation and a lot of publications where we looked at various things. High strength, could we degrade contaminants of emerging concern? And different configurations. We always had a mixing reactor on the left. We always had an upflow biochar packed column. And sometimes we had a second anaerobic upflow packed column. Sometimes we put in an aerobic trickling filter, downflow. And sometimes I had simulated sand filters, sometimes I didn't. Sometimes down there you can't quite see it, but there's a big containment vessel, and above the reactors you didn't see, I had a aeroponics system, which I used to grow off the treated water, tomatoes, bell peppers, and the like. So we did this for like 5 years solid. Along the line, I worked on some demonstration scale projects. Basically, the main concepts here going into demonstration scale. I designed this system. It was built by my friend Kevin, who was he was an engineer in Oregon working for Pacific Biodiesel. And this has the mixing tank, and it has 2 packed bed biochar reactors, both upflow in series. So from my design, he ended up designing how to build it. And you'll see that they are in modular units. Each of them have their own frames. And it was shipped out in a container, and they put it together. They had a forklift, they lifted it up, then we bolted all the pipes together, stainless steel flanges. And it worked very well. We tried it, and we were treating grease trap wastewater. So at this plant, this is where Pacific Biodiesel processed its grease trap waste. And it was trying to collect the oil off the grease trap waste. So they had to heat it up in large towers, and then the oil would go to the top, and then they had the wastewater down below. And the wastewater they were dumping down the drain. And Bob King at that time was anticipating to be charged very high, or not necessarily fines, but extra costs for the high strength nature of the wastewater. And it turned out that he got a waiver for it. So this project, they never really deployed it, but it was designed with them, cost shared by them, and off money that I got from a grant, we split it, to treat their wastewater. Over here was a project I did with Real Green Power and Dennis Furukawa, and he wasn't using biochar. He was using a different packing material that he had licensed from the university. But the goal there was to treat the primary clarifier effluent at the wastewater plant. And this was the anaerobic column, and then this was the aerobic. So you can mix and match these units. This would be an initial mixing tank. We eventually put in biochar in there because the packing material he leased had a lot of problems. It didn't work particularly well. Also, this water was pretty low strength. And it's sort of, you don't quite get the benefit of anaerobic digestion on primary clarifier effluent. It's a little too weak to really justify that whole effort. You don't need to knock it down, but it still worked. And we found that we could replace their plant with about 35 to 40 of these column reactors. Use less energy, but the same amount of space. Point I want to make is I have worked at demonstration scale. I have worked, and the design that I'm going to show you was based on my experience at both sizes in industry. And so the system that I finally designed, which I haven't had built yet, but I have designed it with a colleague who's an engineer, it was really designed to be useful to small scale, small businesses, not necessarily something to necessarily distribute through a massive engineering firm. But frankly, you can build everything in modules, and it could very well be franchised or something like that. I'm really looking to find someone in Hawaii who has a wastewater source of high strength where this would really be useful to them. Maybe they're separated away from wastewater treatment facilities. Maybe they're going to be charged a lot for the high strength wastewater. Maybe they want to have some reactor that breaks down a large pond of wastewater that they have that's high strength, or something like that. So when I finally sat down and I kind of decided to design how we would look, this is a rendering that we did. It starts with the mixing tank. This might be a bit oversized, but the mixing tank serves with a grinding pump. And it is where the initial feed comes in, and it's recycled at a rapid rate through a really strong grinding pump. So you can put in solids and fats and materials like that, and it grinds it down and it separates it. And if you, at the top, there is a way to do an overflow kind of in a cup where the water flows over it and you put screens on it. And you can also adjust the pH there if you need to. You can adjust the temperature if you need to. So it's that initial mixing tank. And then we have a metering pump that pumps out of it. And it's a metering pump that then controls the flow rate through the anaerobic columns. So I'm looking at this, and technically speaking, there's an error. This inlet pipe should go into the bottom of the reactor, or like right around there, because the first anaerobic column is the flow goes up the anaerobic column. It's a packed bed of biochar. And what we do have, though, at the bottom of these reactors is a recycle loop. So we will, once a day, twice a day, as the solids build up and they fall to the bottom, because this packing bed does act kind of like a screen of solids rising. And you will get eventually gravity pull down your solids. And if so they build up, you can pump them back up. You can either pump them back to the main mixing tank, or you can just recycle just to get mixing within the column itself. And then finally, you have an overflow by gravity that goes to the next tank, and it feeds in there and it goes right up to the top. And then you have the clean water come out, and you can either have your gravity go down, or you can, usually this pipe will then go down and it goes into another tank. So we did this exact design at Pacific Biodiesel. You have gas where you can collect off the top. Same thing, we can recycle the solids back either to the first tank or back to the mixing tank, however you think it's best. I usually like to bring them back to the mixing tank. And you have another recycle loop. So it is important to have recycle within each reactor to help with the mixing, because the idea is that usually this feed is somewhat acidic. If you can recycle the wastewater within this column, as the acids are taken up, the pH rises. And so it's a good way to recycle to kind of help readjust and maintain the pH, because a lot of the fats that we found in the grease trap waste was volatile organic acids or fatty acids. And as they got consumed, the pH would actually rise. And that was a good way to get a pH gradient through the reactors that really helped methanogenic communities. So we designed it in the skids, a mixing tank and anaerobic reactor, or 2 anaerobic reactors. We sized it out. There's a support area for your pumps and so forth. You can have one of these, anaerobic followed by an aerobic if you want to, so you can plug and play. You can have as many anaerobic in series as you like, depending upon, are you getting the full BOD reduction or reduction in COD that you need? But it's nice plug and play. Some other advantages. It's a modular design. You can build just a couple of units and you can add on more as time goes on as you need. They can be prefabricated in frames. They fit in containers for shipping. It's a non-permanent installation design. It can stay permanent, but you can also remove it. This keeps you from having to build really large concrete type systems that are then permanent. It can support anaerobic, aerobic configurations as well. Definitely low tech. These pumps can all be analog with dials on them to just control the speeds. One thing I really like, particularly about the anaerobic packed beds with the biochar, is it supports easy shutdown and restart. These films, even when they dry out, the biofilms, when you restart, the reactor kicks up. So you avoid some of the problems with fluidized beds where you have to build up the flocculated sludge. Supports redundancy and easy repair, incremental buy-in, incremental scale up. Expansion is needed. It can definitely knock down high strength feeds. Its big selling point is that this mixing tank followed by this anaerobic or several anaerobic columns can really knock down high strength feed. If you want to add on a trickling filter at the end for polishing, you can. Organic solid dense feeds. With the grease trap waste, this chopper pump really grinded down and it really broke down any of the solids that came in. Some basic dimensions. Here is a skid with the mixing tank and 1 anaerobic reactor. It's roughly 4.3 by 4.3, total area of about 196 feet, 18 meters squared, 200 square feet. And with respect, here is the actual flux. So it's not going to process a lot of water. It's not a really high flow through flux because we're dealing with anaerobic. But I do have plotted here the flux in liters per day per meter squared or gallons per day per meter squared per foot squared. And if you want to do an HRT at around 1, this is good for low strengths. If you really want to go to high strength feeds, I found this system with 5 days, we can knock down some pretty high strength wastewater, in particular the grease trap wastewater. On the y-axis, in terms of liters per day per meter squared, these 3 plots are for a mixing tank and an anaerobic. Here's a mixing tank with 2 anaerobics, and here's a mixing tank plus 3 reactors, 2 anaerobic and an aerobic, for example. And what you find is the fluxes at HRTs of about a day, anywhere from 175 to about 250 liters per day per meter squared. For gallons per day per foot, that's 4 to 6 gallons per day per foot squared. It's the same, at 5 days, we're down around 50 liters per day per meter squared. And the reason you don't get a huge flow through is because you're dealing with high strength and you're treating it anaerobically, where you get a gas stream off of it. And the anaerobic treatment doesn't produce a lot of solids. So that's a big advantage, as opposed to the aerobic systems, which really produce a lot of solids that you then have to take care of. We costed it out. We used rough estimates. We were using a manufacturer in Missouri. We looked at pumps and tanks and so forth. 3 tanks, 1 mixing, 2 ADs. For a high carbon feed, it's just a difference in pumps. You got a few extra pumps, around 220,000, 230,000. If it's a low carbon feed, you wouldn't have to buy the same kind of pumps, basically, to pump the fluids. So that's kind of the pricing. I'll go quickly in these 3 slides. I just want to show you that I did a theoretical study of about 81 anaerobic digesters out there, wastewater anaerobic reactors, that were dealing with all designs, upflow. We had membrane bioreactors, packed bed, USABs, continuous stir tank reactors, anaerobic membranes. I looked through the major ones that were done. And on 3, I did look at metrics. And one of them was as a function of the volumetric organic loading rate that was being fed. We looked at what was the reduction in total COD across all of those papers. And I propose an acceptable range of around 80% reduction in COD based across what I saw most of the literature could achieve. And our systems are above that. I also plotted the volumetric organic loading rate again, kilograms meter cube per day, against the volumetric TOC reduced. That's the volumetric kilograms TOC meter cubed per day. And I did that plot, and the straight line is what you'd expect for complete degradation. And I did a linear fit of all the data I got in the literature to do a proposed acceptable regime. And the idea was anybody's design of any reactor ought to fit within this regime. And again, our reactors fit in with that. And we're competitive with anaerobic membrane reactors and so forth. Same thing, a third metric was the methane yields. Cubic meters per kilogram COD reduced, again, plotted as a function of organic loading rate for all the reactors we found in the literature. And the theoretical upper limit is 0.35 based on calculations and theory. That's the most you could produce. Why are there data points above it? People were measuring their gas production rates and they weren't correcting for temperature back to standard state. If you do correct all of that work, you find they all fall below the 0.35. That just means they were measuring gas rates for gases that were higher temperatures and therefore they had expanded due to the ideal gas law. If you correct them all back down to the same temperature, the same pressure, then you find that they're producing just around 0.35 or below. Our reactors was in there. I thought 0.25, you shouldn't be below it. And we're in that range as well. So that was a way to show that these are competitive. We also did a quick study for a couple of years, not quick, but it was the last one, where we looked at the packed bed anaerobic upflow and the trickling bed down, and we looked at how it dealt with contaminants of emerging concern. And we found that it was able to treat wastewaters highly concentrated with caffeine, estrone, E1, E2, but less so with contaminated with carbamazepine and 17-alpha ethinyl estradiol. So mixed results, but the idea was that in the biofilms they might absorb. And one thing we definitely found was when we spiked with these contaminants, one thing we found is that the biofilms would absorb them. And if they weren't necessarily degrading those contaminants emerging concern that are far more difficult to break down, to digest under anaerobic or even aerobic, you would still get this buffering of the flow, the flux through, because the biofilms would absorb and then slowly release them. So the effluents might still be at low concentrations, even though they weren't being degraded compared to what, and so if you've got a spike coming through of one of these contaminants, these reactors will, at least if they don't address that particular contaminant emerging concern, for the most part, they will slow it down and they will broaden out the exit. So maybe you're at lower concentrations that might be below your restrictions. And this is just a whole list of papers that I published on it to just show that it's backed up with a lot of academic research. And this, if you want to, here's some pictures of the packing materials. This is the biochar that we used. In the trickling filter, we have these large rationing rings. This is some other kind of packing materials that were mixed in with the biochar. This was commercial ribbons you could buy. And that's it. I have 15 minutes. I think I finished on 15 minutes, so I'll answer questions.
Good job. Thank you. The question, just to jump in, the biochar, where did you get that? And it looked perfectly cylindrical, like.
Yeah, so that was that was a tough one because normally speaking, biochar is all broken down because the main markets for it is for a soil amendment. So it already gets ground down. But I found a couple of companies, one in Canada, a Canadian company that had a contract to sell biochar as a coal substitute. So they were making, they were taking biomass, trees, and they were making biochar out of it. So they were using it, and then they use it as a coal substitute. And the Canadian government was basically subsidizing coal substitutes. So that's how they were making money out of making biochar. And they were looking for other markets. And as it turns out, when I got funded on an internal project at the university, we were looking to trial the biochar in a lot of applications, both in the soil and my reactors. And we had a faculty member who had a reactor to make biochar, and he theoretically had a pilot scale one up on campus. He never bothered to tell me that he could never get it to operate. He could never get it permitted to run. So I get the money, and then one day I find out he ain't gonna produce anything more than lunch bags full. And so I had to take away some of his money, which wasn't fun. And then I went and had to go find people outside. And this Canadian company, which was a young, really entrepreneur owner, was willing to actually have his staff, because they take their biochar and then they put it through a chopper, a grinder. And he was willing, they were willing to go take all the pieces that didn't get ground down, and they picked them out by hand force over, you know, a month or two. It was really amazing. So we got that for the Pacific Biodiesel. And then what you saw Dennis holding, it was the largest he could find, but he was spreading it out in this big fiber thing, so I didn't care. If you're going to pack it all together, I think the best thing to do is go to some of these companies in Colorado, because the biochar is now being sold for the pot industry. For all the pot growers, they want biochar.
Huh, interesting.
And Colorado is where you get these gentlemen who companies that are producing biochar. And the idea is you get logs, you have them send logs that have been charred, and then you buy your own grinder and you grind it up, because you're going to want to put in slightly bigger pieces than small ones, because then you're going to get too much packing, particularly if you put in high strength and you start to get that. So it's either that, or I thought about mixing it in with other plastics like wiffle balls that are very porous, and to kind of space it out. You can do little tricks like that. Yeah. But, you know, even if biofilms kind of form within the biochar, it is a membrane that is very permeable. So the water still flows through it. And actually it helps to capture a lot of the colloidals and the solids, and they end up getting degraded. But it's important to have internal recycle to keep the mixing going.
Cool, thank you.
Did I answer your question?
You did, and I did not know about the pot industry. That's good to know. That's funny. It's such a growing field. That could be a huge market just in itself. So yeah, other questions?
Literally a growing field.
Yes, it's a growing field.
I don't have any question, but I have some ideas that I'd like to bounce off you for high strength waste. One is if we expand with the working group, if we expand the number of septic systems in the state, going to be a lot of pumped septage, and that kind of screws up the existing wastewater treatment plants. And I wonder if that's a potential market for you.
Absolutely. Yeah, I've tried from time to time but I never really know who to contact, but that's a perfect substrate for it.
And the counties don't quite know what to do with it. They currently can take some, but if we expanded the number of septic systems, they would be out of luck.
Yeah, so it's a good target for that, because it's a slurry. And that mixing tank is designed to handle the slurries. And it's kind of simple, but when you move it into a packed bed to then clean the water, it starts to become a really nice, simple design.
I think the county wastewater treatments in the Big Island might be a market for that, because I don't think they have the capacity to handle it. Another area I thought of is with the industrial waste, Barbers Point, etc., places where people are producing maybe producing the oil refinery, for example, no longer in operation. There may be some pretty serious industrial waste that would need knocking down. They currently would need pre-treatment, I think, in order to get into the to put their waste into the wastewater treatment system.
Is there a high organic carbon content in those wastes? I would have thought there are more minerals and.
I think it depends on what they're producing. Yeah. So that you need a high carbon content. Is that it?
Well, it's pointless to do anaerobic unless you're knocking down high strength, because the anaerobic cultures can handle big surges in high strength, which would knock out an aerobic system, right? So it's good that's why they can stabilize. If you have a continuous operation, but every once in a while you get from a distillery and you get this big dump of high strength organics, you want to have anaerobic ahead of it to knock it down. And and if you got a low strength wastewater, then you might as well use some of these really good aerobic designs, because, aerobic, it will take low strength and knock it down to really sort of a water that can be discharged, right? Really clean, that meets all the specs. But you can't go into any of these aerobic polishing systems unless you knock down the high strength to begin with. And so if you're really trying to produce water you can discharge, but it's higher strength than primary chlorofluoreffluent, you really do you need to have an upfront unit that is anaerobic to knock that COD or the BOD5 down.
I don't know if these are high strength, but what about commercial aquariums like Maui Ocean Center and Waikiki Aquarium, which is, I think, gone out of business? But they have really high nutrients, I think. But they also have really high volume, so I don't know if they count as high strength.
I have no idea.
Yeah. Okay.
Sorry about that. I've never thought of that.
These are just suggestions for
very good suggestions.
And the other thing that's an advantage is you can shut it down and restart it. Mm-hmm. So, well, advantage isn't the right word. It's a feature, right? It may not be advantage for some people, it may not be needed. But if it's in a place that's going to be intermittent use, then this is a useful feature too. And it doesn't take high tech to run it. Once some people are trained in how to operate it and process it, it becomes fairly plug and play. But the only issue is whether or not you got to adjust the pH in the beginning, because all systems are somewhat pH. And if you have high strength wastewaters, they can get pretty acidic as a feed. But we did trial in this idea on pH control, that if you kind of have a continuous stream that is actually fairly acidic, the first thing you do, the first batch that comes in, you would add in some base, sodium hydroxide, to bring the pH up 6.2, 6.4, so it can run through the column. And what we did in our lab is we would do that, and then we just put the entire mixing tank, one big plug, into the column reactor, and then we ran it for about 10 hours. And the pH rose because the acids start to get consumed and the hydroxyl ions get freed up again. And then we would add in to our feed tank a new aliquot of acidic water or acidic wastewater, and we would recycle that water that had been treated in the primary column. We would recycle it back, and it brought all the hydroxyl ions back, and it actually brought the pH back up. So we got to where once we got going, we never had to do pH control, even though we were bringing in an acidic feed. And I published that paper. It was really, we were real proud of that because we could run for a year and a half without ever having to modify the pH. Because in that first column, the hydroxyls would be freed as the fatty acids were consumed, the acids were consumed. And so the pH would rise. And as the acids got consumed, the hydroxyls were freed. All we had to do was recycle them back. And it was basically like adding a base. It was basically our base pump. It was really pretty cool.
Yeah.
So there, you can get around that. So anyways, the system can be made pretty low tech, which I think really important in wastewater treatment.
And we usually try to stick to an hour, so we're going to kind of wind down. But Wes Wong had to sign off. Wanted me to mention Aquex. I don't know if you've heard of them. It's the Korean company, and they had a pilot project at where was it? Yoko, Schofield?
Schofield, yeah.
Yeah. And so maybe we can follow up with you on that. Wes thought, you should meet with them because they're doing some really interesting stuff. And I'm sure would love to kind of,
Yeah, I had some contact with them. I'd worked with Aqua engineers a lot. I had contacts, and I had said, if you have projects I can work on, that'd be great. And they kind of connected me to them, but they didn't give me any money, and they wanted to use my entire lab for analysis. And it was really ridiculous. One way.
That's
it was solely about that technology that they were going to demonstrate. Good company. I had no problem with that, but I just couldn't be taking students and sending them up there doing the work that they wanted because it did not fit their degree needs at all. Yeah. And, I finally said, well, if you hire these students, then that's fine, but you're going to have to pay for them.
Yeah.
It was a really strange, they were just going to try to give me stuff to write papers with them. It's like, look, these students have a certain set of rights that I can't misuse them. I know of them. The technology was certainly solid. I didn't have any problems with that.
And two very quick questions before we sign off. Jordan was asking if this was where's that question? A batch reactor?
If it's continuous feed or batch.
Yeah, continuous feed or batch.
So either way, you can really load it up, run it. You can just recycle through the anaerobic column for days until it's clean, and then you can just basically wash it out. Or you can run it continuous. And yeah, I think a pig farm might be really useful, as well as I don't know about the grid housing. If the grid housing is actually going to put the solids into a cesspool or septic tank, and then eventually you want to treat that, then I think that might work.
And one thing, any restaurant that has over, I think is it 400 customers per day or more than 5,000 square feet has to recycle compost all of their food. And so a lot of it goes to these piggeries, and these piggeries are often on the west side, a number of them, and they do not make good neighbors. And so, on a final note, I think that might be something to think about, because if we can find something that's more efficient than that, or it can at least, clean the pig waste itself, if it's not an alternative to that, that would be good. But people are dropping out because we usually do hold this to 1 hour. I really want to thank you, Michael, for sharing all your years of research. And this is just something to introduce. So if anybody, you might want to just share your email in the chat. And if anybody wants to follow up, we really encourage that, because this is about introducing people and technologies and getting people together to collaborate. So please feel free to do so. And please share your email. Also, like if you or the CRAP group, if you want to share ideas and suggestions for future speakers, we're always looking for speakers for each month. So on that, thank you again, Michael, and thank you all for joining us.
Thank you very much.
we will see you next week. And Michael, feel free to continue joining us.
Okay. Thank you so much.
Okay. Good night, everyone.
Good night.
Thank you.
Aloha.
Good night. Good to see you all.
Thank you, guys.
Bye, Brooke. Good seeing you.
Good seeing you too.
Night, everyone.
Bye.